The last normal sunrise in human history begins like any other. Coffee brewing in kitchens across the globe. Children walking to school under familiar golden light. Scientists checking their instruments, unaware that the fusion furnace, 93 million miles away, has just gone silent. But we wouldn't know, not yet. Light travels at 186,000 miles per second, the universe's ultimate speed limit. Every photon streaming toward Earth left the sun's surface 8 minutes and 20 seconds ago. Right now, the final wave of solar energy is racing through the vacuum of space, carrying the last warmth our planet will ever receive from its parent star. Picture this moment frozen in time. A businessman in Tokyo steps onto a sunny sidewalk. A farmer in Kansas watches wheat sway in morning light. A child in São Paulo chases shadows in a playground. None of them know they're experiencing the end of an era that began 4.5 billion years ago. The physics are brutally simple. Without nuclear fusion in the sun's core, no new photons are being created. The existing light continues its journey like water flowing through a pipe after the faucet is turned off. For 8 precious minutes, Earth remains bathed in the illusion of normalcy. Think about your morning routine. Checking your phone, making breakfast, stepping outside. The sun appears perfectly normal overhead, a brilliant disk of light and heat. Birds sing. Flowers turn their faces toward the warmth. Photosynthesis continues in every leaf and blade of grass. The whole planet operates on borrowed time. Observatories around the world detect nothing unusual. Solar telescopes show a normal stellar surface. Radio dishes receive regular electromagnetic signatures. Even our most sensitive instruments see no change because the change hasn't reached us yet. The sun might as well be functioning perfectly. But in deep space, the reality is different. If you could somehow position yourself exactly halfway between Earth and Sun, you'd witness an invisible boundary racing toward our planet. Behind this line, the solar wind carries no new energy. Ahead of it, the last solar particles stream toward home. The countdown has begun, though no clock can measure it. 8 minutes, 20 seconds. Enough time to make a sandwich, walk to the corner store, have a brief conversation. Enough time for millions of people to start their days completely unaware that daylight will never come again. As the final moments tick away, the sun appears unchanged in our sky. Solar panels continue generating electricity. Satellites orbit normally. Weather patterns follow their usual paths. Earth's magnetic field deflects space radiation just as it has for billions of years. The irony is profound. The most catastrophic event in human history will arrive silently, invisibly, without warning. No sirens will sound. No emergency broadcasts will interrupt regular programming. The end of our solar-powered world will simply appear as the gentle fading of a summer afternoon. At exactly 8 minutes and 20 seconds after the sun stops shining, the last photon will strike Earth's atmosphere. From that moment forward, our planet begins its journey into endless night. But for now, in these final precious minutes, the world continues spinning under light that has already become a memory. The last normal day is ending. We just don't know it yet. The sky begins to dim like a theatre slowly lowering its lights. But this isn't sunset. This is something unprecedented in human experience. At first, people notice nothing. The change comes gradually, almost imperceptibly. The sun appears to fade, like looking at it through increasingly dark sunglasses. Children playing outside might glance up, wondering if clouds are gathering. Adults might check their watches, confused by the dimming light. Within minutes, the illusion crumbles. The sun, that constant bright disk we take for granted, grows visibly darker. Its brilliant white light fades to yellow, then orange, then red. But unlike a normal sunset, the sun doesn't move. It simply dies in place, wherever it happens to be in your local sky. For people experiencing daytime when the darkness arrives, the transformation is surreal. Imagine standing in your backyard at noon as shadows begin to lengthen, despite the sun remaining directly overhead. The light takes on an eerie twilight quality that belongs neither to day nor night. The first stars become visible. At what should be broad daylight, pinpricks of light emerge in the darkening sky. Confused birds return to their roosts. Streetlights flicker on automatically as their sensors detect falling light levels. Traffic systems switch to night mode. The entire technological infrastructure of human civilization begins responding to conditions it was never designed to handle. Within an hour, the transition is complete. The sun has become a dark disk, barely visible against the star-filled sky. For the first time in Earth's 4 billion-year history, the planet experiences true darkness on its daylight side. The psychological impact is immediate and profound. Humans evolved under the rhythm of day and night, light and darkness. Our circadian rhythms, our sleep cycles, our very sense of time depends on solar cues. Suddenly, those cues vanish. The natural order of existence simply stops. Children cry in confusion. Adults stand in the streets, looking up at stars visible at midday. Phone networks overload as millions try to contact family and friends. Social media explodes with videos of the darkening sky. Emergency services are flooded with calls from people convinced something is terribly wrong. But perhaps most unsettling is the silence that follows. As the last solar light fades, a peculiar quiet settles over the world. Not the comfortable darkness of evening, but something alien and wrong. The absence of warmth becomes noticeable almost immediately. Without the sun's constant energy input, the atmosphere begins its long slide toward equilibrium with the cold vacuum of space. Temperature sensors worldwide register the first measurable drops within hours. The change is subtle at first, maybe a degree or two, but it's relentless. Earth has become a cooling rock in space, radiating away its stored heat with nothing to replace it. Photosynthesis stops immediately. Every green plant on Earth, from tiny algae to massive redwood trees, suddenly finds itself in an impossible situation. Evolutionary programming spanning billions of years tells them to capture sunlight and convert it to energy. But there is no sunlight to capture. The oxygen generators of our planet go silent. Not just the obvious ones like forest trees, but the invisible billions of marine phytoplankton that produce most of our breathable air. The complex chemical reactions that maintain our atmosphere's composition begin to shift. Yet humans adapt with remarkable speed. Within hours, cities become islands of artificial light. Backup generators roar to life. Emergency broadcasts explain the situation to frightened populations. The species that once lived in caves and hunted by firelight begins to remember how to survive in darkness. The world has changed forever, but we don't yet understand how dramatically. Earth holds heat like a massive stone warmed by a campfire. Even after the flames die, the stone remains warm for hours. Our planet possesses what physicists call thermal mass, the ability to store and slowly release energy. This simple property becomes humanity's brief reprieve from immediate catastrophe. The numbers tell a story of temporary mercy. Earth's average surface temperature is 15 degrees Celsius. Without the sun's constant input of energy, our planet begins radiating this heat into the void of space at a predictable rate. But like that cooling stone, the process takes time. Think of Earth as a gigantic heat reservoir. The oceans alone contain enough thermal energy to power human civilization for thousands of years. Rock and soil store heat in their molecular structure. Even the atmosphere itself is a vast container of thermal energy, invisible but substantial. During the first few hours after darkness falls, most people notice only a slight chill in the air. It feels like a cool evening, nothing more. Thermal sensors register drops of just a few degrees. Children still play outside, though parents call them in earlier than usual. The physics of heat loss follows Stefan Boltzmann's law, a mathematical relationship describing how objects radiate energy. Earth loses heat proportional to the fourth power of its temperature. This creates a curve that starts gradually but accelerates over time. The first degree takes hours. The 10th degree takes much less time. Regional variations create a complex thermal map. Tropical oceans cool slowly, their vast water masses releasing stored energy like natural heaters. Desert regions with less thermal mass cool more quickly. Mountain peaks lose heat faster than valleys. Coastal areas stay warmer longer than inland locations. Urban areas become heat islands in the global cooling. Concrete and asphalt store heat collected during billions of previous sunny days. Buildings themselves become temporary radiators, releasing energy accumulated over decades of construction. Cities might stay warmer than surrounding countryside for weeks. Underground temperatures change hardly at all. Subway systems, basements, and natural caves maintain their steady temperatures, completely insulated from the surface cooling. Geologists know that descending just a few feet below ground reveals remarkably stable thermal conditions. These underground spaces become valuable resources. The first day passes almost normally. People wear sweaters instead of t-shirts. Heating systems work a bit harder. Energy consumption increases as homes and businesses compensate for falling ambient temperatures. But nothing feels catastrophic yet. Smart thermostats worldwide register the change. Weather stations record identical patterns across the globe. Steady, relentless temperature decline. Climate models predict the trajectory, but the immediate experience feels manageable. Earth is spending its thermal savings account, and the balance remains substantial. Ice forms first in the coldest regions. Mountain peaks and polar areas see frost within hours. But most populated areas experience nothing more dramatic than unusually cool weather. The temperature drops feel like seasonal changes rather than planetary catastrophe. Night offers no relief, but also no additional cooling. Without solar heating, day and night become meaningless distinctions. The entire planet exists in perpetual darkness, cooling at the same steady rate, regardless of Earth's rotation. By the end of the first day, global temperatures have dropped perhaps 5 degrees Celsius. Uncomfortable, but not unbearable. People adapt by adding layers, turning up heaters, staying indoors. The human capacity for adjustment masks the severity of what's beginning. But the clock keeps ticking. Earth's thermal mass is finite. The heat that took 4 billion years to accumulate will dissipate in a time frame measured in human lifespans, not geological ages. In biology classrooms around the world, students learn a simple equation. Sunlight plus carbon dioxide plus water equals sugar plus oxygen. This reaction, photosynthesis, powers virtually all life on Earth. When the sun stops shining, this ancient chemical factory shuts down immediately. Plants don't have fuel tanks or backup generators. They live moment to moment on solar energy, converting light into chemical energy faster than a Formula One pit crew changes tires. Every green leaf is a solar panel, every cell a microscopic power plant. When darkness falls, the entire system simply stops. The process happens invisibly, but universally, from the Amazon rainforest to suburban lawns, from ocean phytoplankton to potted houseplants. Every photosynthetic organism on Earth suddenly finds itself in an impossible situation. Their evolutionary programming spans billions of years, but none of it prepared them for permanent darkness. Think about a typical oak tree. Its leaves contain millions of chloroplasts, each one a sophisticated machine for capturing light and converting it to usable energy. These biological solar panels operate with remarkable efficiency, better than most human technology. But they cannot function without light, any more than a solar calculator can work in a closet. The immediate response varies by species. Some plants have energy reserves, stored starches and sugars accumulated during previous sunny days. These reserves might sustain them for days or weeks, like a battery slowly draining. But the battery cannot recharge. Once depleted, the plant faces starvation. Tropical rainforests, those green powerhouses of oxygen production, begin to struggle within hours. The massive trees that tower above the canopy depend on constant sunlight to feed not just themselves, but entire ecosystems of smaller plants growing in their shadows. Without new energy input, the complex web of forest life starts to unravel. Grass lawns and agricultural crops face similar challenges. Cornfields that should be converting sunlight into grain simply stop growing. Wheat plants halt their production of the seeds that feed billions of people. Rice paddies, vegetable gardens, and fruit orchards become biological museums, their living contents preserved temporarily by stored energy. Ocean plants present a more complex picture. Kelp forests along coastlines begin to weaken as their huge brown fronds can no longer photosynthesize. But the real crisis occurs among phytoplankton, microscopic plants that float near the surface of seas and oceans worldwide. These tiny organisms produce more oxygen than all land plants combined. Phytoplankton have virtually no energy reserves. They live entirely in the present, capturing sunlight and immediately converting it to growth and reproduction. When darkness arrives, their populations begin to crash within hours. The biological foundation of marine food webs starts to collapse before larger organisms even notice. Indoor plants offer a fascinating contrast. Houseplants sitting under artificial lights continue photosynthesis, though at reduced rates. Office buildings with skylights and grow lights become accidental preserves for photosynthetic life. These small refugia demonstrate what might be possible with sufficient artificial lighting. The oxygen crisis develops slowly but inevitably. Photosynthesis doesn't just feed plants, it produces the oxygen that animals breathe. With photosynthesis stopped globally, oxygen production ceases while oxygen consumption continues. Every breath taken by every animal begins depleting an atmospheric resource that can no longer be replenished. Forest fires, where they occur, accelerate the process. Burning vegetation consumes oxygen rapidly while producing carbon dioxide, but most plants die quietly, slowly consuming their stored energy reserves while contributing nothing new to atmospheric oxygen. Agricultural scientists worldwide face a stark realization. The entire human food system depends on plants converting sunlight into edible calories. With photosynthesis stopped, crop production becomes impossible. Stored grain might feed humanity for months, but no new food can be grown without artificial lighting systems that don't yet exist at necessary scales. The green world is dying, silently and invisibly, but the effects will soon become impossible to ignore. Nature doesn't surrender without a fight. As the first week of darkness unfolds, the natural world deploys every survival strategy developed over millions of years of evolution. The results create a planet-wide emergency response unlike anything in Earth's recorded history. Trees begin cannibalizing themselves. Without sunlight for photosynthesis, they start breaking down stored starches and sugars, converting internal reserves into energy for basic survival. Deciduous trees that might normally prepare for winter begin dropping leaves immediately, reducing energy demands. Evergreens maintain their needles, but reduce metabolic activity to barely detectable levels. Animals respond with instinctive behavior patterns triggered by the endless darkness. Diurnal species, programmed for daylight activity, become confused and disoriented. Birds attempt migration patterns in random directions, their internal navigation systems unable to process the absence of solar cues. Some simply hunker down, entering torpor states usually reserved for winter. Nocturnal animals initially benefit from the change. Owls hunt continuously, without the constraint of daylight hours. Bats find themselves in a world tailored to their acoustic navigation abilities. But even these night-adapted species soon discover that permanent darkness brings unexpected challenges as their prey species become depleted. The temperature drop creates its own ecological cascade. As global temperatures fall below freezing during the first week, plant cells begin suffering damage from ice crystal formation. Tropical species, never adapted for cold, start dying immediately. Temperate zone plants fare better initially, but even they lack mechanisms for surviving the sustained cold that's coming. Hibernating animals face a cruel paradox. Species like bears and groundhogs depend on stored fat reserves to survive winter dormancy. but their biological clocks aren't programmed for permanent winter. Some emerge from hibernation too early, driven by confused circadian rhythms, only to find a world with no food sources available. Aquatic ecosystems show remarkable resilience initially. Fish populations remain largely unaffected during the first week, protected by water's thermal mass. Ocean temperatures drop slowly, giving marine life time to adapt. But the foundation of aquatic food webs, photosynthetic plankton, begins declining immediately, creating a time bomb for ocean ecosystems. Soil organisms retreat deeper underground, following temperature gradients toward the Earth's core. Earthworms burrow below the frost line. Beneficial bacteria and fungi reduce activity but don't immediately die. The soil itself becomes a refugee camp for microscopic life-seeking warmth and stability. Pollinating insects face immediate crisis. Bees, butterflies, and other pollinators depend on flowering plants for both food and navigation cues. With flowers shutting down and temperatures dropping, these crucial ecosystem workers begin dying en masse. Their loss ensures that even if sunlight returned, plant reproduction would face severe limitations. Seed banks activate across the planet. Plants that invested energy in seed production during previous growing seasons unknowingly prepared for exactly this catastrophe. Seeds lie dormant in soil and seed pods, their metabolism reduced to nearly zero. These biological time capsules could theoretically wait decades for favorable conditions to return. Predator-prey relationships shift dramatically. With many herbivore species stressed by cold and lack of food, carnivores initially find abundant weak prey. But this advantage is temporary. As herbivore populations crash, predators face starvation themselves. The entire food web begins collapsing from the bottom up. Symbiotic relationships strain under the new conditions. Trees can no longer provide sugar to their fungal partners in root systems. Coral reefs begin bleaching as their algae partners die without light. These ancient partnerships, refined over millions of years, simply cannot adapt to permanent darkness quickly enough. Desert ecosystems prove surprisingly resilient. Species already adapted to extreme conditions and scarce resources show better survival rates than their temperate counterparts. Cacti and other succulents, with their efficient water storage and slow metabolism, outlast plants from more hospitable environments. By week's end, the global ecosystem has reorganized itself around survival rather than growth. Energy conservation becomes the universal strategy. The planet's biological systems settle into what might be called emergency mode, burning through accumulated resources while waiting for conditions that will never improve. Nature's emergency measures buy time, but they cannot solve the fundamental problem. Without energy input from the sun, the biological world is running on borrowed time. The moment sunlight fails, human civilization's greatest achievement becomes its salvation. Cities, those dense concentrations of people and technology, transform into beacons of light in a darkening world. But they also become pressure cookers of resource consumption and social tension. Power grids worldwide face immediate stress tests. Electricity demand surges as every building compensates for lost solar heating. Air conditioning systems switch to heating mode. Streetlights activate during daytime hours. Office buildings illuminate spaces normally lit by windows. The energy infrastructure, designed for predictable daily cycles, suddenly operates at peak demand around the clock. Emergency response systems activate automatically. Hospital backup generators roar to life, ensuring critical care continues. Emergency services deploy with disaster protocols, treating the situation like a massive power outage that never ends. Fire departments prepare for increased heating-related incidents as people turn to alternative heat sources. Urban heat islands become literal lifesavers. Cities naturally run warmer than surrounding areas due to concrete's heat retention, industrial activity, and dense population. This normally problematic effect suddenly provides crucial thermal advantages. Downtown areas might stay livable days longer than suburban or rural regions. Traffic patterns change immediately. Without natural light, vehicle headlights become essential for navigation even during former daylight hours. Street lighting systems, designed to operate 12 hours daily, now face continuous operation. Some cities begin rationing electrical power, creating rolling blackouts to preserve fuel supplies. Food distribution networks face unprecedented challenges. Grocery stores, supplied by complex logistics chains, begin experiencing shortages within days. Frozen and refrigerated foods require constant electricity. Supply chains dependent on agricultural regions that can no longer produce crops start breaking down rapidly. Apartment buildings with central heating systems create warm refugia for thousands of residents. High-rise structures, normally energy-intensive, become efficient, shared heating systems. Neighbors who barely spoke before begin cooperating on resource sharing and mutual aid. Building superintendents become crucial community leaders, managing heating systems that mean survival. Public transportation systems struggle with new realities. Subway systems, naturally warmed by underground locations and electrical systems, become popular gathering places. Bus services continue operating, but face increased passenger loads as people seek any form of heated transportation. Airport terminals, with their large heating systems and emergency power supplies, become unofficial warming centers. Social services mobilize rapidly. Homeless shelters expand capacity to accommodate people whose homes lack adequate heating. Schools with large heating systems become community centers. Libraries, with their combination of books for entertainment and heating systems for comfort, see unprecedented crowds. Communication networks experience massive overload. Cell phone towers struggle with unprecedented usage as people seek information and contact family. Internet services slow under the weight of millions seeking news updates. Social media becomes crucial for organizing community responses and sharing resources. Economic activity transforms overnight. Businesses dependent on natural lighting shut down or operate under expensive artificial illumination. Energy companies become the most valuable enterprises. Hardware stores sell out of generators, batteries, and heating equipment. Fuel prices spike as demand for heating oil, natural gas, and gasoline surges. Urban gardens and rooftop farms, small but growing food sources in many cities, install emergency grow lights where possible. These efforts remain limited by available electricity, but demonstrate potential pathways for maintaining some food production. Indoor farming facilities with artificial lighting become incredibly valuable resources. Waste management systems face new pressures. Increased heating means more ash and combustion byproducts. Sewage systems might freeze in some regions, creating sanitation challenges. Garbage collection continues, but with modified schedules to conserve fuel for collection vehicles. Cultural institutions adapt to new roles. Museums with climate control systems become gathering places. Concert halls and theatres provide both entertainment and warm spaces for community gathering. Religious buildings expand their traditional role as community refuges. Within a week, cities have reorganized around survival priorities. The same dense infrastructure that usually creates complexity now provides efficiency in resource distribution and heating. Urban areas become humanity's best hope for organized survival, islands of warmth and cooperation in an increasingly cold world. But the energy reserves that power these urban lifelines are finite, and the clock is ticking toward much greater challenges ahead. Physics obeys no negotiation. Earth's surface temperature, maintained at life-supporting levels for billions of years, begins an inexorable slide toward the cosmic background temperature of -270 degrees Celsius. The mathematics are as precise as they are terrifying. Heat flows from warm objects to cold ones, always and without exception. Earth, now warmer than the surrounding vacuum of space, radiates its thermal energy away at a rate determined by fundamental physical laws. The planet becomes a cooling ember in the cosmic fireplace, gradually reaching equilibrium with its frigid surroundings. The Stefan Boltzmann equation describes this process with mathematical precision. Energy loss equals the fourth power of temperature multiplied by surface area and a physical constant. This relationship creates a cooling curve that starts gradually but accelerates as temperatures drop. Early cooling is slow, later cooling becomes precipitous. Regional cooling rates vary dramatically based on thermal mass and geographic features. Ocean areas cool slowly, their vast water masses storing and releasing heat like planetary radiators. Continental interiors cool faster, lacking the thermal buffer of large water bodies. Mountain ranges lose heat rapidly due to their exposure and thin air, while valleys retain warmth longer. The first month sees average global temperatures drop approximately 30 degrees Celsius. This might sound gradual, but represents an unprecedented rate of planetary cooling. No natural climate change in Earth's history has preceded this quickly. The planet is experiencing thermal shock on a geological scale. Atmospheric circulation patterns begin changing as temperature gradients shift. Without solar heating creating different temperatures between equator and poles, the driving force behind weather systems weakens. Wind patterns become more chaotic and unpredictable. Traditional weather forecasting becomes nearly impossible. Ocean currents, driven partly by temperature differences, start to slow. The Gulf Stream, which keeps Western Europe warmer than its latitude would suggest, begins weakening. Similar thermal currents worldwide face disruption. These changes affect regional climates in complex ways, sometimes slowing cooling in some areas while accelerating it in others. Lakes freeze completely within weeks. Starting with shallow ponds and progressing to larger bodies of water, the transformation creates new landscapes of ice. Lake effect snow disappears as the temperature difference between water and air equalizes. Ice fishing becomes impossible, not because of regulation, but because fish cannot survive in frozen solid water. Soil temperatures drop below freezing at increasing depths. Plants with root systems in frozen ground cannot absorb water, even if liquid water existed. Agricultural regions become wastelands of frozen earth, impossible to cultivate even with heated greenhouse protection. The growing season becomes permanently ended. Building heating systems work harder, but fight a losing battle. As outside temperatures plummet, the energy required to maintain indoor comfort increases exponentially. Heating bills, for those still receiving them, become astronomical. Many buildings simply cannot maintain livable temperatures despite maximum heating system operation. Snow begins falling globally as atmospheric moisture condenses and freezes. Tropical regions experience snow for the first time in their geological history. Desert areas, normally too dry for snow, see precipitation as atmospheric water vapor freezes out of the increasingly cold air. The world becomes uniformly white. Permafrost extends far beyond its normal Arctic boundaries. Ground that has been frozen for thousands of years in polar regions sets the template for what Earth is becoming. Permanently frozen ground extends toward the equator week by week, creating new tundra conditions across previously temperate regions. Urban heat islands provide temporary relief, but cannot resist the overall trend. Cities stay warmer than their surroundings, but the difference narrows as ambient temperatures continue falling. Eventually, even the densest urban areas must surrender to the planetary cooling trend. The psychological impact of watching thermometers fall daily becomes profound. People track temperature drops like countdown timers to catastrophe. Weather reports become exercises in documenting planetary death rather than predicting tomorrow's conditions. By the end of the first month, Earth has begun its transformation from a living world to a frozen wasteland. The great cooling has momentum now, an unstoppable physical process that will continue until thermal equilibrium with space is achieved. The race between human adaptation and planetary cooling has begun in earnest. The death of forests happens not with dramatic crashes, but with spreading silence. Trees that have stood for decades or centuries begin dying from the inside out, their biological processes slowing like watches winding down. The transformation creates a haunting quiet that settles over landscapes, once filled with the sounds of living ecosystems. Photosynthesis, the process that built these forests over millions of years, becomes impossible. Trees begin consuming their stored energy reserves. breaking down starches and sugars accumulated during previous growing seasons. Like marathon runners depleting their glycogen stores, trees start burning their own tissues to maintain basic cellular functions. Different tree species respond according to their evolutionary strategies. Deciduous trees, adapted for seasonal energy storage, initially survive longer. Their normal autumn leaf drop becomes permanent as they shed energy-consuming foliage immediately. Evergreens maintain their needles initially, but reduce metabolic activity to barely measurable levels. Root systems, invisible but crucial, begin failing as soil temperatures drop below freezing. Tree roots cannot absorb water from frozen ground, creating drought conditions even in areas with abundant ice and snow. The transportation system that moves water from soil to leaves simply stops functioning. Forest understory plants die first. Smaller plants with minimal energy reserves cannot compete with massive trees for available stored nutrients. Ferns, wildflowers, and shrubs that normally grow in forest shadows begin dying within weeks. The complex layered structure of forest ecosystems starts collapsing from the ground up. Animal life dependent on forests faces immediate crisis. Squirrels find that nut-bearing trees have stopped producing. Birds discover that insect populations are crashing as their food sources disappear. Deer and other herbivores encounter forests where browse plants are dying or already dead. Symbiotic relationships strain under impossible conditions. Trees cannot provide sugars to their fungal partners in underground root networks. These mycorrhizal relationships, essential for forest health, break down as neither partner can fulfill their role. The underground internet that connects forest trees through fungal networks goes silent. Logged forests and forest management areas face unique challenges. Tree farms designed for lumber production become worthless as growing trees cease growth permanently. Reforestation projects halt as seedlings cannot survive without photosynthesis. Decades of forestry planning become obsolete overnight. Tropical rainforests, the most biodiverse ecosystems on Earth, suffer catastrophic collapse. These complex communities depend on rapid cycling of nutrients and energy. With primary production stopped, the intricate food webs supporting thousands of species begin unraveling. The loss of rainforest biodiversity becomes permanent within weeks. Boreal forests in northern regions initially show more resilience. Trees adapted to harsh winters and short growing seasons possess survival strategies that serve them temporarily. But even these hardy species cannot survive permanent winter conditions with no prospect of returning warmth. Fire suppression becomes unnecessary, but also impossible. Dead and dying forests would normally present extreme fire hazards, but falling temperatures and increasing moisture from snow eliminate fire risk. Forests become wet, frozen graveyards of standing timber. Seed production, crucial for forest regeneration, stops immediately. Trees cannot spare energy for reproduction when struggling for basic survival. Seeds already produced might remain viable in cold storage for years, but new seed production ceases. Even if conditions improved, forest regeneration would face severe limitations. Carbon cycling, one of forests' crucial environmental functions, reverses direction. Instead of absorbing carbon dioxide through photosynthesis, dying forests begin releasing stored carbon as they decompose. This process is slowed by cold temperatures, but not stopped, gradually changing atmospheric composition. Forest products industries face immediate obsolescence. Logging operations can harvest existing timber, but no new growth replaces what is cut. Paper production, lumber manufacturing, and other forest-dependent industries begin planning for permanent shutdown as their renewable resource becomes finite. Urban forests and parks follow the same trajectory as wild forests, but with some advantages. City trees might survive longer due to urban heat islands and potential artificial lighting from nearby buildings. Street trees and park vegetation receive more attention from human caretakers, desperately trying to preserve green spaces. Wildlife corridors connecting forest fragments become refugee pathways as animals flee dying woodlands. But these corridors lead nowhere, as all forests face the same fate. The migration routes that normally allow seasonal animal movement become death marches to equally devastated destinations. By the end of the first month, the world's forests have begun their transformation from living ecosystems to frozen monuments. The silence spreads across landscapes where wind through leaves once created natural music, leaving only the quiet whisper of falling snow. Food webs, those intricate biological networks linking all life on Earth, begin collapsing with mathematical precision. Starting with the disappearance of primary producers, the cascade of extinction moves upward through each feeding level like dominoes falling in slow motion. Herbivores face the first crisis. Deer, rabbits, and countless other plant-eating animals discover that their food sources are dying or already dead. Grass stops growing. Leaves become scarce. Seeds and nuts, normally stored by trees for reproduction, are depleted as trees consume their own reserves for survival. Large herbivores suffer first due to their massive caloric requirements. A single deer needs pounds of plant matter daily. Cattle, horses, and elk require even more. With fresh vegetation unavailable and stored plant foods quickly consumed, these animals begin starving within weeks. Their size, normally an advantage, becomes a liability. Smaller herbivores might survive longer by being more efficient with limited resources. Rabbits and rodents can subsist on smaller quantities of available food. Some switch to eating bark, roots, and other normally rejected plant parts. But even these adaptations provide only temporary reprieve, as all plant matter becomes increasingly scarce. Carnivores initially benefit from abundant weak prey. Predators find easy hunting as starving herbivores become slower and less alert. Wolf packs encounter deer herds that barely flee. Birds of prey discover rodents weakened by hunger. For a brief period, meat-eaters experience unprecedented abundance. But predator success creates its own problem. Overhunting by desperate carnivores accelerates herbivore population crashes. Predators lack the evolutionary wisdom to conserve prey for future meals. They consume available food as quickly as possible, ensuring their own future starvation. Scavengers face a complex situation. Dead animals become abundant as herbivore populations crash, providing carrion feeders with temporary plenty. Vultures, crows, and other scavengers initially thrive. But decomposition slows dramatically in freezing temperatures, creating preserved carcasses that remain accessible longer than normal. Insect populations crash rapidly due to their dependence on living plants and their sensitivity to temperature changes. Bees find no flowers to pollinate. Butterflies discover that their caterpillar stage cannot survive without fresh leaves. Beetles that depend on tree bark and wood find that their host trees are dying. Aquatic food webs show more complex patterns. Fish initially remain relatively unaffected as water temperatures change slowly. But marine and freshwater plankton, the microscopic foundation of aquatic ecosystems, begin dying immediately when photosynthesis stops. This creates a delayed but inevitable collapse of fish populations. Birds experience species-specific challenges. Seed-eating birds find their food sources depleted as plants stop producing new seeds. Insect-eating birds discover that their prey species are crashing. Migratory birds face the additional challenge of navigation without normal environmental cues. Omnivores possess temporary advantages over specialists. Animals that eat both plants and meat can switch food sources as availability changes. Bears, pigs, and some rodents can adapt their diets to focus on whatever remains available. But even flexible eating habits cannot overcome the general collapse of food production. Parasite populations face unique pressures. External parasites often depend on healthy host animals that maintain normal body temperatures. Internal parasites might benefit initially as hosts' immune systems weaken, but face ultimate extinction when host populations crash completely. Pet and livestock populations become entirely dependent on stored human food supplies. Dogs, cats, cattle, and chickens cannot forage for natural foods that no longer exist. These animals effectively join the human population in competing for finite stored resources. Decomposer organisms experience dramatically changed conditions. Bacteria and fungi responsible for breaking down dead organic matter work more slowly in cold temperatures. This slows nutrient cycling, but also preserves organic matter longer, creating temporary food sources for organisms capable of consuming dead plant and animal material. Zoo animals present tragic examples of ecosystem collapse in miniature. Facilities designed to maintain diverse species from around the world discover that specialized diets become impossible to provide. Herbivorous species require fresh vegetation that cannot be grown. The world's carefully preserved biodiversity faces extinction in captivity, as well as in wild habitats. By the second month, the mathematical inevitability becomes clear. With primary production ended and stored biological energy finite, every food web on Earth must collapse. The only question is the timing and order of species extinction. The hunger chain, built over millions of years of evolution, breaks permanently within weeks. Life's greatest achievement, the complex web of interdependence that sustained the biosphere, unravels in the face of endless winter. Water covers 71% of Earth's surface, creating the largest thermal reservoir on the planet. This vast liquid blanket has regulated Earth's temperature for billions of years. But even the oceans cannot resist the relentless physics of planetary cooling. Seawater freezes at -2 degrees Celsius due to its salt content, lower than pure fresh water, but still well above the temperatures Earth is approaching. The thermal mass of the oceans means this freezing process will take months rather than weeks. But the timeline is accelerating as heat radiates away into space. Surface waters freeze first, starting in polar regions and gradually expanding toward the equator. Pack ice, normally seasonal in Arctic and Antarctic waters, becomes permanent and begins spreading. The visible edge of ocean ice advances daily, creating new coastlines of solid water. Deep ocean temperatures remain stable initially, protected by the enormous thermal capacity of vast water volumes. Underwater currents continue flowing, distributing heat from deeper waters toward the surface. But this circulation gradually weakens as temperature differences that drive ocean currents begin to disappear. Marine ecosystems face immediate disruption. Phytoplankton, the microscopic plants that form the foundation of ocean food webs, die immediately when photosynthesis becomes impossible. These tiny organisms produce more oxygen than all terrestrial plants combined, and their loss begins changing oceanic chemistry within days. Coastal areas experience the most dramatic changes. Harbors and ports begin freezing, trapping ships in ice. Ferry services halt as routes become blocked. Fishing fleets find themselves locked in frozen harbors, unable to reach fishing grounds that are becoming increasingly barren anyway. Tidal patterns continue, but ice formation complicates their effects. Frozen surface water creates barriers that redirect tidal flows. Coastal flooding patterns change as ice dams alter water movement. Some areas experience higher tides as water is forced through narrower channels between ice formations. Coral reefs face immediate bleaching as their symbiotic algae die without sunlight. These ecosystems, among Earth's most diverse, begin collapsing within days. Tropical coral reefs, never adapted for cold water, face additional stress as ocean temperatures drop below their survival thresholds. Fish populations initially remain stable due to their mobility and the slow temperature change in deeper waters. Many species move toward warmer deep water regions or migrate toward areas where thermal vents provide heat. But the collapse of oceanic food webs ensures that fish populations cannot maintain their numbers long term. Whale migrations become confused as normal temperature gradients disappear. These massive mammals depend on temperature differences to guide their seasonal movements. Without these thermal cues, whale populations become disoriented, potentially stranding in areas that will become uninhabitable. Seabird populations crash rapidly as their food sources disappear. Penguins, perfectly adapted for ice conditions, initially seem advantaged, but soon discover that the fish they depend on are becoming scarce. Other seabirds lose access to nesting areas as islands become covered in permanent ice. Ocean shipping faces increasing difficulties as traditional routes become blocked by ice. Arctic shipping routes, normally opened by global warming, become impassable again. Commercial shipping companies begin rerouting vessels toward equatorial regions where liquid water persists longer. Submarine activity becomes crucial for understanding oceanic changes. Military and research submarines can operate under ice covers, providing data about conditions beneath frozen surfaces. These underwater observations become humanity's primary source of information about oceanic conditions. Coastal cities face flooding followed by ice as tidal surges freeze in place. Venice might experience its worst flooding ever, followed by permanent ice covering. Coastal erosion stops as waves can no longer reach shorelines, but ice expansion creates new forms of geological pressure on coastal structures. Ocean thermal energy conversion systems, designed to generate electricity from temperature differences in seawater, become useless as thermal gradients disappear. Offshore wind farms face icing problems that make maintenance impossible. Ocean-based renewable energy systems fail when needed most. Marine agriculture, including kelp farming and offshore fish farming, becomes impossible as growing conditions disappear. Seaweed cultivation requires photosynthesis and liquid water. Fish farming requires feeding fish with food sources that no longer exist in natural systems. The chemistry of seawater begins changing as ice formation concentrates dissolved salts in remaining liquid water. This creates pockets of extremely salty, dense water that sinks and alters circulation patterns. The ocean becomes stratified in new ways that affect both chemistry and biology. By the third month, significant portions of oceanic surface area have frozen solid. The thermal engine that has driven Earth's climate for billions of years is shutting down. The planet's greatest reservoir of liquid water begins its transformation into a solid, frozen shell. The oceans that gave birth to life on Earth begin their conversion into monuments of ice, preserving but no longer supporting the biological diversity they once nurtured. The global food system, engineered to feed 8 billion people, faces immediate obsolescence. Agricultural regions that produce humanity's calories cannot function without photosynthesis. The mathematics of starvation become as predictable as they are terrifying. Crop production stops instantly. Cornfields in Iowa, wheat plains in Kansas, rice paddies in Asia all halt their growth simultaneously. Plants in various stages of development, from seedlings to near-harvest crops, begin consuming their stored energy reserves rather than producing new food. The growing season ends permanently. Greenhouse operations provide humanity's only agricultural hope. Indoor growing facilities with artificial lighting can maintain photosynthesis, but at enormous energy costs. A greenhouse producing food for one person might consume as much electricity as 50 normal households. The economics make large-scale greenhouse agriculture nearly impossible. Livestock face immediate feed shortages. Cattle, pigs, and chickens depend on grain and hay produced by photosynthesis. With no new feed production, farm animals begin competing directly with humans for stored food supplies. Many farmers begin slaughtering livestock immediately to preserve grain for human consumption. Food storage and distribution systems strain under new demands. Grain elevators designed for seasonal storage suddenly contain the entirety of future food supplies. Refrigeration systems require constant electricity to preserve perishable foods. Cold storage becomes more important than production for the first time in agricultural history. Seed banks take on unprecedented importance. Agricultural research stations worldwide store genetic material from thousands of crop varieties, originally intended for breeding programs and disaster recovery. These seeds become humanity's only hope for future food production if conditions ever improve. Urban agriculture transforms from hobby to necessity. Rooftop gardens and vertical farms in cities install grow lights where possible, becoming crucial food production sites. Community gardens organize to maximize food output from limited spaces and energy resources. Every square foot of growing space becomes precious. Fertilizer plants shut down as their products become unnecessary. With no crops to fertilize, the chemical industry supporting agriculture becomes obsolete overnight. Petroleum-based fertilizers, previously essential for high-yield agriculture, join fossil fuels in having no immediate utility for food production. Harvest operations accelerate desperately. Farmers work around the clock to collect whatever crops are ready, using artificial lighting to extend working hours. Grain combines operate continuously, racing against time to gather the final harvest humanity will see. Storage facilities overflow with this last bounty. Food processing plants operate at maximum capacity to preserve final harvests. Grain mills work continuously to convert wheat into storable flour. Fruit processing facilities race to can and preserve perishable foods. Every apple becomes precious. Every grain of wheat must be preserved carefully. Agricultural machinery manufacturers retool for different purposes. Tractors designed for planting become useful only for transportation. Harvesting equipment processes the final crop, but will never be needed again. The mechanical infrastructure of farming becomes obsolete except for its metal components. International food trade becomes frantic. Countries with large grain surpluses attempt to trade with nations lacking adequate food reserves. But transportation systems face their own fuel limitations. The global network that normally distributes food according to economic demand reorganizes around survival priorities. Fishing industries experience temporary abundance followed by collapse. Commercial fishing vessels can harvest existing fish populations, but these populations cannot reproduce successfully in collapsing marine ecosystems. Overfishing becomes both inevitable and self-defeating as desperate humans deplete oceanic protein sources. Food rationing begins in most countries within weeks. Governments implement emergency distribution systems designed to make stored food supplies last as long as possible. Caloric calculations determine policy as administrators attempt to balance immediate survival against long-term starvation. Black markets in food emerge rapidly. People with access to stored food supplies begin trading with those lacking adequate reserves. Luxury foods become worthless, while basic calories command extraordinary prices. A bag of rice might be worth more than a car. Nutritional deficiencies appear quickly in populations lacking diverse stored foods. Vitamin C deficiency causes scurvy within months. Protein deficiencies lead to kwashiorkor and marasmus. Populations dependent on fresh fruits and vegetables face immediate health crises from malnutrition. Food riots and distribution conflicts begin as scarcity becomes apparent. Grocery stores empty within days of panic buying. Government control of food distribution becomes essential for preventing social collapse. Military forces often manage food warehouses and distribution points. By the end of the second month, humanity has consumed the majority of easily accessible stored foods. Grain reserves intended to last until the next harvest must now sustain populations indefinitely. The agricultural abundance that supported human civilization becomes a rapidly diminishing memory. The final harvest is complete, and there will never be another one. 8 billion people begin learning to survive on the finite food supplies that remain. Human civilization, that delicate construction of laws, customs, and mutual cooperation, faces stresses it was never designed to handle. As resources become scarce and survival instincts override social conventions, the fabric of society begins showing tears that could become fatal ruptures. Government structures strain under unprecedented demands. Emergency powers activated during the crisis grant officials broad authority to manage resources and maintain order. Democratic processes slow or halt as decision-making shifts from debate to immediate crisis management. Constitutional rights conflict with survival necessities as authorities make decisions unthinkable during normal times. Economic systems collapse and reorganize simultaneously. Currency becomes meaningless when goods cannot be purchased at any price. Stock markets close indefinitely as normal investment logic becomes irrelevant. Barter systems emerge as people trade tangible goods for immediate survival needs. Social hierarchies invert rapidly. Wealthy individuals discover that money cannot purchase non-existent goods. People with practical skills, food supplies, or energy resources become the new elite. Social status shifts from wealth accumulation to resource control and survival capabilities. Migration patterns create massive population movements. People in cold climates attempt to move toward warmer regions or areas with geothermal heating. Cities with nuclear power plants attract refugees seeking heat and electricity. Populations congregate around any reliable energy source, creating overcrowding and resource competition. Law enforcement faces impossible challenges. Police departments must maintain order while their officers worry about their own family's survival. Crime patterns shift as people steal heating fuel and food rather than luxury goods. Traditional justice systems cannot function when survival overrides legal considerations. Religious institutions experience both increased attendance and philosophical challenges. Churches, mosques, and temples become warming centers as much as places of worship. Religious leaders struggle to provide comfort and explanation for a catastrophe outside normal theological frameworks. Faith communities organize mutual aid while questioning divine purpose. Educational systems shut down as schools become heating shelters and fuel becomes too precious for transportation. Universities close as both students and faculty focus on immediate survival rather than long-term learning. The transmission of human knowledge faces interruption for the first time in centuries. Healthcare systems strain under new demands while losing basic capabilities. Hospitals become warming centers for vulnerable populations. Medical supplies face shortages as production and distribution systems fail. Healthcare workers must choose between professional duties and family survival needs. Communication networks become crucial but energy dependent. Internet services slow as data centers require enormous electricity for operation. Cell phone networks face overload as everyone seeks information and family contact. Ham radio operators become vital links for communities as commercial communication systems fail. Community organization emerges at local levels. Neighborhoods form mutual aid societies to share resources and coordinate heating. Local leaders organize rationing systems and work assignments. Small-scale democracy flourishes even as large-scale governments struggle with crisis management. Generational conflicts intensify as young and old people face different survival challenges. Elderly individuals require more heating and medical care, but possess useful skills and knowledge. Young people have energy for physical labor, but lack experience with non-technological survival methods. Urban versus rural tensions develop as city dwellers attempt to move to areas with better resource access. Rural communities resist outsiders who might deplete limited local resources. Geographic isolation becomes both protective and limiting as transportation systems fail. Professional military forces take on civilian support roles. Soldiers distribute food and manage refugee centers rather than conducting traditional military operations. Military logistics systems become crucial for civilian survival. The distinction between military and civilian authority blurs as emergency powers expand. Mental health crises multiply as people process the enormity of permanent change. Psychologists and counselors treat unprecedented levels of anxiety, depression, and trauma. Support groups form organically as communities help members cope with loss of normal life expectations. Cultural preservation efforts begin as people realize that many aspects of human civilization might be lost permanently. Libraries become crucial repositories, not just of books, but of practical knowledge. Museums shift focus from displaying artifacts to preserving essential cultural information. International relations transform as national boundaries become less relevant than resource access. Countries with geothermal energy or large food reserves become attractive migration destinations. International law faces challenges when normal diplomatic processes cannot address survival-level resource competition. By the third month, human society has reorganized around survival priorities rather than traditional economic and political structures. The social contract underlying civilization has been rewritten by necessity, creating new forms of human organization adapted to permanent crisis conditions. The pressure is building toward either renewed cooperation or complete social breakdown. Which direction human society takes will determine whether civilization survives the transition to a sunless world. Beneath Earth's surface lies salvation. Geothermal energy, powered by radioactive decay in the planet's core and residual heat from planetary formation, provides an energy source completely independent of solar input. Regions blessed with geothermal activity become humanity's lifeboats in the cosmic catastrophe. Iceland emerges as perhaps humanity's most survivable location. The island nation sits atop the mid-Atlantic ridge, where volcanic activity provides abundant geothermal energy. Reykjavik's geothermal heating system, originally built for comfort and efficiency, becomes a life support system for the population. Yellowstone National Park transforms from tourist destination to potential refuge site. The park's extensive geothermal features, including hot springs and geysers, provide heat sources that could warm surrounding areas. The underground thermal plumbing that creates Old Faithful could support human survival through indefinite winter. New Zealand's North Island offers another geothermal sanctuary. Rotorua's thermal features and the country's geothermal power plants provide heat and electricity completely independent of weather conditions. The nation's geographic isolation becomes an advantage when migration pressures overwhelm other regions. The Philippines, Indonesia, and other volcanic island chains possess scattered geothermal resources. These areas might support small populations indefinitely, though their limited size restricts the number of people they can sustain. Remote volcanic islands become incredibly valuable real estate. California's geysers region, the world's largest geothermal field, becomes a crucial survival zone. The power plants already operating there could expand their mission from electricity generation to direct heating for refugee populations. San Francisco's proximity to geothermal resources becomes a major survival advantage. Japan's volcanic activity provides scattered geothermal opportunities across the island chain. Hot springs resorts, originally recreational facilities, become essential survival infrastructure. The country's advanced geothermal technology and volcanic geology combine to create multiple survival possibilities. Turkey's Pamukkale and similar geothermal regions offer heating potential for substantial populations. The ancient Romans recognized these thermal resources. Modern survivors rediscover their life-sustaining properties. Thermal springs that once attracted tourists become magnets for climate refugees. Individual hot springs and smaller geothermal features become locally crucial. Natural hot springs in places like Colorado, Montana, and Wyoming could warm small communities through the crisis. Even modest geothermal resources become invaluable when all other heating depends on finite fuel supplies. Underground thermal gradients provide heat even in areas without obvious surface geothermal activity. Deep basements and underground structures access ground temperatures that remain stable year-round. Subway systems in major cities become surprisingly warm refuges as they tap into geothermal heating. Geothermal greenhouse operations represent the future of agriculture. Facilities that use underground heat to warm growing spaces could continue food production indefinitely. These installations become humanity's agricultural hope, producing food through artificial lighting powered by geothermal electricity. Hot spring communities organize around thermal resources the way desert societies organize around oases. Natural thermal features dictate settlement patterns as people cluster around heat sources. Traditional property rights give way to survival-based resource sharing in these thermal communities. Geothermal power plants require technical expertise to maintain, but offer substantial heating capacity. Engineers and technicians become crucial community members as their skills determine whether geothermal resources remain accessible. Technical knowledge becomes as valuable as the thermal resources themselves. Volcanic activity creates both opportunities and dangers. Active volcanoes provide heat, but also pose eruption risks. Hot lava creates thermal zones, but threatens anyone who ventures too close. Volcanic regions require careful balance between accessing heat and avoiding geological hazards. Construction around geothermal features accelerates as people build shelters near heat sources. Traditional architecture gives way to designs that maximize thermal capture from underground sources. Insulation becomes crucial for conserving geothermal heat once it's captured. Resource conflicts develop around the most valuable geothermal sites. Areas that could support hundreds of people attract thousands of desperate refugees. Management of geothermal resources becomes a matter of life and death, requiring careful allocation to prevent overuse or conflict. Competition between communities near geothermal resources leads to cooperation or conflict depending on local leadership and resource abundance. Some geothermal areas become models of mutual aid and resource sharing. Others experience territorial disputes as groups fight for access to thermal energy. Scientific research into geothermal resource development accelerates, as survival depends on maximizing thermal energy extraction. Drilling techniques and heat pump technology become crucial for accessing deep geothermal resources. Engineering expertise focused on thermal management becomes humanity's most valuable skill set. Transportation networks reorganize around connecting population centers with geothermal resources. Supply chains focus on moving people and goods between thermal refugia rather than supporting traditional economic activities. Geothermal regions become the nodes around which remaining human civilization organizes. By the fourth month, geothermal regions have become humanity's primary population centers. These islands of heat in a cooling world represent the difference between survival and extinction for millions of people. The geography of human habitation has been redrawn around Earth's internal heat sources. Nuclear power plants, originally built to generate electricity, transform into humanity's backup suns. These facilities, designed with multiple safety systems and backup power sources, become islands of heat and light in a world growing darker and colder every day. France leads the world in nuclear dependence, with reactors generating 70% of the nation's electricity. This nuclear infrastructure, previously seen as environmental risk, becomes France's salvation. Nuclear plants provide both electricity and waste heat that can warm surrounding communities indefinitely. The physics work in humanity's favor. Nuclear reactors generate enormous amounts of thermal energy, most of which is normally released as waste heat through cooling towers. This waste heat can warm buildings, power heating systems, and maintain livable temperatures for large populations near reactor sites. Reactor cooling systems require continuous operation to prevent meltdowns, meaning nuclear plants must maintain full staffing and technical support even during global crisis. This necessity creates job security and community stability around nuclear facilities when other industries collapse completely. Multiple redundant safety systems in nuclear plants include diesel generators and battery backup systems designed to operate independently for extended periods. These emergency power systems provide heating and electricity, even if main power grids fail, creating energy security unavailable in other locations. Nuclear plant workers become among the most valuable people in post-catastrophe society. Their technical expertise ensures continued reactor operation and heat generation. These specialists must remain at their posts, not just for their own survival, but for the survival of thousands of people depending on reactor heat. Countries with multiple nuclear plants possess distributed survival advantages. The United States, with its 93 commercial reactors, has numerous potential refuge sites scattered across the nation. Each reactor site could theoretically support several thousand people indefinitely with proper resource management and community organization. Naval nuclear reactors on submarines and aircraft carriers provide mobile nuclear heating sources. These vessels could park near coastal cities and provide heating and electricity to surrounding populations. Military nuclear assets become humanitarian resources in the survival economy. Nuclear waste storage facilities, normally isolated for safety reasons, become valuable for their thermal output. Radioactive materials generate continuous heat through decay processes, creating warming potential that could last for centuries. Areas near nuclear waste storage sites become unexpectedly livable. Research reactors at universities and laboratories add to the nuclear heating network. These smaller facilities cannot support as many people as commercial power plants, but provide survival options for educated populations who can maintain and operate sophisticated nuclear systems. Reprocessing facilities and uranium enrichment plants contribute additional nuclear heating capacity. These industrial facilities, designed for nuclear fuel processing, generate substantial thermal energy that could be redirected toward heating residential and agricultural areas. Nuclear icebreakers, designed to operate in Arctic conditions, become floating survival platforms. These vessels can navigate frozen seas while providing heat and electricity to coastal populations. Their nuclear reactors could operate for decades without refueling, making them incredibly valuable resources. Construction accelerates around nuclear facilities as people recognize their survival value. New housing developments spring up within heating range of reactor sites. Traditional urban planning gives way to survival-based settlement patterns organized around nuclear heat sources. Security concerns around nuclear facilities intensify as they become crucial survival resources. Protecting nuclear plants from sabotage or resource conflicts becomes essential for community survival. Armed guards and restricted access zones ensure that nuclear heating remains available for authorized populations. Nuclear fuel supplies determine long-term survival prospects. Most reactors contain fuel sufficient for months or years of continued operation. Some reactor designs can operate for decades without refueling. The longevity of nuclear fuel becomes a critical factor in site selection for survival communities. Technical challenges include maintaining reactor operation with reduced technical support staff and limited supply chains for replacement parts. Nuclear engineers must become generalists capable of handling all aspects of reactor operation and maintenance. The technical complexity of nuclear systems becomes both an advantage and a vulnerability. Medical facilities near nuclear plants gain importance for treating radiation exposure and maintaining health of nuclear workers. Hospitals with nuclear medicine departments become crucial for supporting the technical workforce required for reactor operation and heat generation. Transportation networks prioritize connections between nuclear sites and population centers. Supply routes focus on moving people and essential goods between nuclear oases rather than supporting traditional economic activities. Nuclear facilities become the anchors for reorganized human geography. Agricultural applications of nuclear heat include greenhouse operations and food processing facilities powered by reactor thermal energy. Nuclear-heated greenhouses could provide fresh vegetables through artificial growing seasons, making nuclear sites agricultural centers as well as population refuges. International cooperation around nuclear technology becomes essential as nations share expertise and resources for maintaining reactor operation. Nuclear engineers from different countries collaborate to ensure continued operation of humanity's thermal lifelines. By the fifth month, nuclear facilities have become humanity's primary energy sources and population centers. These nuclear oases represent technological civilization's best hope for maintaining some semblance of advanced society through the permanent winter. The Earth's crust offers refuge from surface catastrophe. Underground spaces, insulated from temperature extremes and powered by geothermal gradients, become humanity's new frontiers. What begins as emergency shelter evolves into permanent underground civilization. Existing subway systems provide immediate underground infrastructure. New York's subway tunnels, London's underground, and similar transit networks become residential spaces as surface temperatures plummet. These tunnels, designed for transportation, transform into underground neighborhoods with their own heating, lighting, and waste management challenges. Natural cave systems expand their historical role as human shelters. Mammoth Cave in Kentucky, Carlsbad Caverns in New Mexico, and similar formations offer natural underground spaces with stable temperatures. Cave communities organize around existing geological features, adapting underground spaces for long-term habitation. Underground shopping centers and parking garages become instant residential complexes. Mall concourses designed for retail shopping accommodate sleeping areas and common spaces. Underground parking structures provide shelter space that can be divided into private living areas while maintaining community gathering spaces. Basement interconnection projects create underground neighborhood networks. Buildings with existing basements begin connecting through tunnels and passages, creating underground communities that span entire city blocks. These networks allow movement between buildings without surface exposure to cold temperatures. Mine shafts and tunnels offer deep underground access to geothermal heating. Abandoned mines provide ready-made underground spaces with access to Earth's thermal gradient. Active mining operations shift from resource extraction to community heating as their deep underground locations become valuable residential real estate. Construction techniques adapt to underground living requirements. Ventilation systems become crucial for maintaining air quality in enclosed underground spaces. Lighting systems must operate continuously without natural light sources. Water and waste management require engineering solutions adapted to underground environments. Underground agriculture develops through artificial lighting and thermal management. Basement growing operations and tunnel farming provide food production capability independent of surface conditions. Root vegetables and mushroom cultivation become primary underground food sources, requiring minimal artificial lighting. Hydroponics and aquaponics systems flourish in underground environments where temperature and lighting can be controlled precisely. These systems provide both food production and psychological benefits of maintaining living plants in otherwise sterile underground environments. Engineering challenges include air circulation, water supply, and waste disposal for large underground populations. Ventilation shafts must circulate fresh air without losing thermal energy. Water systems require pumping and treatment capabilities adapted to underground use. Sewage disposal becomes complex when surface treatment facilities are unavailable. Community organization develops unique characteristics in underground settlements. Leadership structures emerge based on technical expertise and resource management skills. Social dynamics change when entire communities live in confined underground spaces, requiring cooperation for basic survival. Security considerations include controlling access to underground communities and managing resource sharing among underground populations. Underground settlements develop their own protocols for admitting new residents and managing conflicts in confined spaces where interpersonal disputes become survival issues. Communication systems adapt to underground environments where cell phone signals cannot penetrate and internet connections require specialized infrastructure. Ham radio networks and hardwired communication systems become essential for maintaining contact between underground communities and coordinating resource sharing. Psychological support becomes crucial for populations adapting to permanent underground living. Mental health services address depression, anxiety, and claustrophobia associated with losing access to natural light and open spaces. Community activities and recreational programs help maintain morale in challenging living conditions. Underground utilities require independent power generation and distribution systems. Generators and battery systems provide electricity for lighting, heating, and ventilation. Power management becomes critical when fuel supplies are limited, and electrical demand includes life support systems. Health considerations include preventing disease transmission in crowded underground conditions and maintaining nutrition when food variety is limited. Medical facilities in underground communities focus on preventive care and managing chronic conditions with limited pharmaceutical supplies. Resource storage and management become crucial skills in underground communities. Food storage requires techniques adapted to underground conditions without refrigeration. Water storage and treatment ensure safe drinking supplies when surface water sources may be frozen or contaminated. Trade networks develop between underground communities as different settlements specialize in different survival skills and resources. Underground communities might trade food production capacity for technical expertise or fuel supplies for medical services. Cultural activities adapt to underground environments as communities maintain human traditions despite changed living conditions. Music, storytelling, and artistic expression help preserve human culture during extended underground habitation. Libraries and educational programs ensure knowledge transmission to children born underground. Transportation between underground settlements develops through tunnel networks and surface travel between underground access points. Supply lines connect different underground communities, creating regional networks of mutual support and resource sharing. By the 6th month, underground communities have evolved from emergency shelters into functioning underground societies. These subterranean cities represent a new form of human civilization, adapted to permanent residence beneath Earth's surface. Agriculture without sunlight becomes an exercise in applied physics and desperate ingenuity. The few remaining farmers must reinvent food production using artificial lighting, alternative energy sources, and growing techniques that humanity has never needed to scale up for survival. LED grow lights become humanity's substitute sun. These energy-efficient lights can provide specific wavelengths that plants need for photosynthesis, but the electricity requirements are staggering. Growing food for one person using artificial lighting might consume more electricity than powering several homes, creating impossible energy economics for large-scale agriculture. Greenhouse operations adapt from commercial production to survival agriculture. Existing greenhouse facilities install heating systems and artificial lighting where possible, becoming humanity's primary food production centers. These controlled environments allow precise management of temperature, humidity, and lighting conditions necessary for plant growth. Hydroponic systems maximize food production per unit of space and energy. Growing plants in nutrient solutions rather than soil allows more precise control of growing conditions while using less water and space than traditional agriculture. Vertical hydroponic systems stack growing areas to maximize production in limited space. Mushroom cultivation emerges as the most energy-efficient food production method. Mushrooms don't require photosynthesis, growing instead by decomposing organic matter. Mushroom farms can operate in complete darkness, using only heat for optimal growing conditions, making them ideal for energy-constrained food production. Sprouting operations provide fresh nutrition with minimal energy requirements. Seeds and beans can produce nutritious sprouts using only warmth and moisture, requiring no artificial lighting. Sprouting systems can provide fresh vitamins and minerals when other vegetables become unavailable. Root vegetable storage becomes crucial for maintaining food supplies. Potatoes, carrots, and other root vegetables store well without refrigeration in cool, dark conditions. Underground storage facilities maintain these foods through their natural dormancy periods, extending food availability. Composting and organic waste recycling support continued growing operations. Food scraps and organic waste become valuable resources for producing growing medium and nutrients for continued plant production. Waste management becomes agriculture as every organic material gets recycled into food production systems. Aquaculture adapts to indoor conditions as fish farming becomes a protein source independent of outdoor ecosystems. Fish tanks and recirculating aquaculture systems provide protein production that requires heating but no artificial lighting. Fish processing and preservation become essential skills. Seed preservation and propagation ensure future growing potential. Seed banks and seed saving become critical skills as farmers maintain genetic diversity and growing capacity for future food production. Seeds become currency in the new survival economy. Energy management determines agricultural feasibility. Solar panels, where available, power greenhouse operations during remaining daylight hours. Wind power, battery storage, and generator systems support agricultural energy needs. Energy efficiency becomes the primary constraint on food production capacity. Soil management adapts to indoor growing conditions. Potting soil, compost, and growing medium must be preserved and recycled carefully. Soil health becomes more important when natural soil processes cannot replenish nutrients. Indoor soil management requires different techniques than outdoor agriculture. Pest management changes when natural predator populations disappear. Greenhouse operations must control insect pests without natural ecosystem balance. Integrated pest management becomes crucial for protecting limited food production from insect damage. Water systems adapt to indoor food production requirements. Irrigation systems, water recycling, and moisture management become essential for maximizing water efficiency in food production. Water quality and treatment ensure plant health when water sources may be limited. Pollination becomes a manual process when natural pollinators disappear. Hand pollination and artificial pollination techniques ensure fruit and seed production for crops that require pollination. This labor-intensive process becomes necessary for maintaining food production. Nutrition management focuses on producing foods that provide essential vitamins and minerals, often lacking in stored foods. Fresh greens and vegetables provide nutrition that cannot be obtained from grain and preserved food supplies. Growing operations prioritize nutritional value over quantity. Community-supported agriculture develops around shared greenhouse and growing operations. Community groups pool resources to build and maintain food production facilities. Shared labor and resource management make small-scale agriculture feasible where individual farming would be impossible. Technical expertise becomes crucial for maintaining artificial growing systems. Agricultural engineers and horticulturists become essential community members. Knowledge of plant biology, growing techniques, and equipment maintenance determines agricultural success. Food processing and preservation maximize the value of limited agricultural production. Canning, dehydrating, and fermentation techniques preserve harvests for extended storage. Processing facilities work to maximize nutrition and shelf life of foods produced through energy-intensive growing methods. Distribution systems connect food production sites with population centers. Transportation and logistics focus on moving fresh foods from growing operations to communities that cannot produce their own food. Fresh food becomes a luxury commodity requiring careful distribution management. By the 7th month, artificial agriculture has evolved from experimental technique to survival necessity. These last farmers represent humanity's only hope for continued food production in a world where natural agriculture has become impossible. The mathematics of survival become brutally clear as energy resources dwindle and population pressures exceed available resources. Geographic location, resource access, and community organization determine survival probability with algorithmic precision. Geographic advantages create survival hierarchies. Populations near geothermal features, nuclear power plants, or coal deposits possess thermal energy for heating. Coastal areas with access to tidal energy or wind power maintain some electricity generation. Mountainous regions with hydroelectric facilities retain power sources when fuel supplies are depleted. Population density becomes inversely related to survival probability. Rural areas with lower population density can support their residents longer with available resources. Urban areas, despite better infrastructure, face resource shortages more quickly due to higher population concentrations and limited storage capacity per person. Resource stockpiles determine community survival duration. Areas with grain storage facilities, fuel depots, or strategic reserves can maintain their populations longer than regions dependent on daily resource delivery. Military installations and emergency supply centers become survival advantages for nearby populations. Technical expertise within communities affects survival probability significantly. Communities with engineers, doctors, and skilled technicians can maintain complex systems longer and more efficiently. Educational levels and technical knowledge become survival advantages when complex infrastructure requires maintenance and operation. Age demographics influence community survival prospects. Populations with higher percentages of working-age adults possess more labor capacity for survival tasks. Communities with many elderly or very young residents face greater resource consumption and reduced work capacity for survival activities. Economic inequality transforms into survival inequality as wealth becomes meaningless, but resource access remains crucial. Previously, wealthy individuals without survival skills or resource stockpiles face disadvantages. People with practical skills and resource access become the new elite, regardless of previous economic status. Community organization and leadership determine resource allocation efficiency and conflict resolution. Well-organized communities with effective leadership allocate resources more efficiently and maintain morale during crisis. Communities lacking organization face resource waste and internal conflicts that reduce survival probability. Climate zones' starting conditions affect survival timelines significantly. Tropical regions start with warmer temperatures and longer cooling periods. Arctic regions already adapted to cold conditions have infrastructure and cultural knowledge for survival in low temperatures. Infrastructure condition and energy independence determine how long communities can maintain livable conditions. Areas with renewable energy systems, efficient buildings, and redundant infrastructure systems maintain habitability longer than regions dependent on centralized energy and resource distribution. Food production capability affects medium-term survival prospects. Communities with greenhouse facilities, food processing capabilities, or agricultural expertise can extend food supplies longer than areas dependent entirely on stored foods. Seed stocks and growing equipment become survival advantages. Medical facilities and healthcare access affect population survival rates significantly. Communities with hospitals, medical supplies, and healthcare professionals can maintain population health longer when stress, cold exposure, and malnutrition create health challenges. Transportation access determines resource mobility and community connectivity. Areas with fuel reserves, vehicle maintenance capabilities, and transportation infrastructure can move resources and people more effectively. Isolated communities without transportation face resource limitations but avoid resource competition. Water supply security affects basic survival requirements. Communities with independent water sources, water treatment capabilities, or groundwater access maintain essential services longer than areas dependent on centralized water systems that require continuous energy input. Military and security capabilities determine ability to defend resources against desperate populations from less fortunate areas. Communities with security forces, defensive positions, or weapons stockpiles can protect their resources from refugee populations and resource raids. Cultural factors, including cooperation traditions, mutual aid practices, and community solidarity, affect resource sharing and collective survival. Communities with strong social bonds and mutual aid traditions organize survival efforts more effectively than areas lacking social cohesion. Survival probability calculations become grim mathematical exercises. Demographers and sociologists attempt to model survival rates based on resource availability, population size, energy access, and community organization factors. These models predict survival percentages ranging from single digits in resource-poor areas to 50% in optimal locations. Government response and resource allocation policies affect regional survival rates. Emergency management systems, military aid, and resource redistribution programs influence which communities receive survival support. Political factors determine resource allocation when supplies become insufficient for universal survival. International migration and refugee movements redistribute population toward areas with better survival prospects. Border security and immigration policies determine whether regional advantages remain available to local populations or become diluted by refugee influxes seeking survival opportunities. Disaster preparedness and survival skills within communities determine adaptation success to changed conditions. Communities with emergency preparedness traditions, survival knowledge, and practical skills adapt more successfully to resource constraints and infrastructure failures. By the 8th month, survival probability maps show clear geographic and demographic patterns. The distribution of who lives and who dies follows predictable patterns based on resource access, community organization, and environmental advantages, creating a new geography of human survival. As immediate survival consumes human energy, far-sighted individuals and institutions begin the crucial work of preserving human knowledge, culture, and genetic diversity for potential future recovery. These preservation efforts could determine whether humanity emerges from the crisis intact or irreparably diminished. seed banks transform from agricultural research tools into humanity's biological insurance policy. The Svalbard Global Seed Vault, built into Arctic permafrost, contains genetic material from virtually every food crop variety known to exist. This doomsday vault becomes literally humanity's hope for eventual agricultural recovery. Digital preservation efforts accelerate as the internet and electronic storage systems face energy constraints. Organizations work frantically to download and preserve essential human knowledge onto physical storage systems that can survive without continuous power. Priority goes to practical survival information, medical knowledge, and technical documentation. Library preservation initiatives focus on maintaining physical books and documents when digital systems become unreliable. Librarians organize efforts to preserve essential knowledge in formats that require no electricity to access. Books on medicine, engineering, agriculture, and basic survival become the most valuable literature. Cultural preservation projects document human artistic and cultural achievements before cultural institutions lose power and heating. Museums photograph collections and create physical catalogues. Musicians record performances. Writers document cultural knowledge and traditions that might otherwise be lost when survival takes priority over culture. Scientific knowledge preservation ensures that technical understanding accumulated over centuries remains available for future application. Research institutions compile essential scientific information into physical formats. Technical drawings, formulas, and procedures get printed and preserved for future use, when research capabilities might be restored. Genetic diversity preservation extends beyond crop seeds to include human genetic material and endangered species preservation. Sperm banks, egg banks, and tissue samples preserve genetic diversity that could be crucial for future population recovery. Zoos and research institutions preserve genetic material from species facing extinction. Educational material preservation focuses on information needed to transmit essential knowledge to future generations. Textbooks, technical manuals, and educational resources get preserved in formats accessible without electrical power. Teaching materials ensure that surviving children can receive education when formal educational systems resume. Medical knowledge documentation becomes crucial as pharmaceutical and medical technology industries collapse. Medical professionals compile treatment protocols, drug information, and surgical procedures into reference materials that can guide medical care when advanced medical systems are unavailable. Technical documentation preservation ensures that complex systems can be rebuilt when resources become available. Engineering drawings, manufacturing processes, and maintenance procedures for essential infrastructure get preserved for future reconstruction efforts. Industrial knowledge gets archived for eventual societal rebuilding. Historical documentation efforts record the catastrophe itself for future study and understanding. Historians and journalists document human responses, survival strategies, and social changes during the crisis. This historical record could guide future crisis response and provide learning opportunities for recovered civilization. Artistic and cultural expression continues despite survival pressures as humans maintain psychological health through creative activities. Art, music, and literature created during the crisis provide emotional outlet and cultural continuity. These cultural products preserve human creativity during the darkest period in human history. Language preservation becomes important as isolated communities risk losing linguistic diversity. Efforts to document languages, dialects, and cultural knowledge ensure that linguistic heritage survives even if communities are displaced or dispersed by survival pressures. Institutional knowledge preservation focuses on maintaining organizational knowledge and procedures that enable complex societies to function. Government procedures, legal frameworks, and administrative knowledge get documented for eventual use when governmental and social institutions can be re-established. Professional expertise preservation ensures that skilled knowledge remains available for future application. Master craftsmen, skilled technicians, and professional experts document their knowledge and train apprentices where possible. Professional knowledge that takes years to develop gets preserved through documentation and training programs. Communication systems for future coordination help preserve networks between surviving communities for eventual coordination of recovery efforts. Ham radio networks, message relay systems, and communication protocols maintain connections between separated communities and facilitate future coordination. Population records and genealogical information preservation helps maintain family connections and genetic diversity tracking through the crisis period. Records of births, deaths, and family relationships provide foundation for social reconstruction when communities can reunify. Resource mapping and documentation identifies locations of valuable resources that could support future recovery efforts. Maps of fuel deposits, mineral resources, equipment stockpiles, and infrastructure locations provide valuable information for eventual reconstruction activities. Survival strategy documentation records successful and unsuccessful approaches to crisis survival for future application. Technical innovations, resource management techniques, and community organization methods get documented for use by other communities and future crisis response. Recovery planning begins even during crisis as communities plan for eventual reconstruction and societal rebuilding. Plans for agricultural restoration, infrastructure rebuilding, and social reconstruction provide frameworks for organized recovery when resources permit rebuilding efforts. By the 9th month, preservation efforts have created a distributed archive of human knowledge and culture spread across surviving communities. These preservation efforts represent humanity's investment in its own future, ensuring that recovery is possible when conditions permit rebuilding civilization. The planet's transformation reaches its inevitable conclusion. Earth's surface temperature approaches the cosmic background temperature of negative 270 degrees Celsius, just 3 degrees above absolute zero. The world becomes an ice sculpture of its former self. Atmospheric composition changes dramatically as gases begin freezing out of the air. Water vapor, already scarce due to earlier freezing, becomes virtually non-existent. Carbon dioxide begins solidifying at negative 78 degrees Celsius, falling as dry ice snow. Eventually, even nitrogen and oxygen will freeze, creating a surface covered by layers of solidified atmosphere. Ocean surfaces complete their transformation to solid ice. The thermal mass that once moderated Earth's climate becomes a frozen monument to the planet's warmer past. Ice sheets extend from polar regions toward the equator until no liquid water remains on the surface. The entire hydrosphere becomes solid. Geological processes slow dramatically in the extreme cold. Rock contraction from thermal stress creates new fracture patterns in surface geology. Tectonic activity continues deep underground, but surface geological processes essentially stop. Earth's surface becomes geologically static. Wind patterns cease as temperature differences disappear and atmospheric density increases. Without thermal gradients to drive air movement, weather becomes non-existent. The dynamic atmospheric systems that created Earth's climate patterns go quiet. Snow accumulation continues as water vapor sublimates from ice surfaces and refreezes elsewhere. This process gradually redistributes surface ice, creating unique geological features from sublimation and redeposition processes. Snow depths accumulate to unprecedented levels in some areas. Pressure changes affect atmospheric behavior as cold air becomes denser and atmospheric pressure increases. The thicker atmosphere affects how sound travels and how remaining heating systems operate. Atmospheric pressure at sea level increases significantly. Surface features become permanently preserved under layers of ice and frozen atmosphere. Forests, cities, and geological features disappear beneath accumulating frozen precipitation. The surface topography becomes simplified as valleys fill with ice and snow. Underground temperatures remain stable due to geothermal gradients and thermal inertia. Locations more than a few meters below ground maintain temperatures warmer than surface conditions. The underground becomes the only habitable zone on the planet. Biological processes cease almost entirely, except in heated refugia. decomposition stops in frozen conditions, preserving organic matter indefinitely. Bodies of water and organic materials become permanently frozen monuments to Earth's biological past. Crystal formation creates new types of surface features as different atmospheric gases freeze under varying conditions. Layers of frozen nitrogen, oxygen, and carbon dioxide create stratified deposits with unique optical and physical properties. Light reflection changes dramatically as Earth's surface becomes uniformly white and reflective. The planet's albedo approaches unity, meaning virtually all incoming light gets reflected back to space. Earth becomes visible from space as a brilliant white sphere. Gravitational effects remain unchanged despite surface transformation. Earth's mass and orbital characteristics continue normally. The planet maintains its orbit around the now dark Sun, completing yearly cycles that have no seasonal meaning. Magnetic field effects continue as usual since they originate from Earth's molten core, which remains unaffected by surface cooling. The magnetosphere continues protecting the planet from solar wind and cosmic radiation. Cosmic ray effects become more significant without atmospheric protection from lighter gases that have frozen out. Increased radiation reaches the surface, though this poses little threat to the already lifeless surface environment. Tidal effects continue from gravitational interaction with the Moon, though they affect solid ice rather than liquid oceans. Ice sheets experience tidal stress, creating fracture patterns and ice movements similar to but different from ocean tides. Thermal equilibrium approaches, but never quite reaches absolute perfection due to internal heat from radioactive decay and residual planetary formation energy. Earth's core temperature remains largely unaffected by surface conditions, maintaining geothermal gradients. Surface chemistry becomes dominated by sublimation and deposition processes as different materials transition between solid and gas phases under extreme temperature conditions. Chemical reactions virtually cease except in areas with geothermal heating. Astronomical visibility changes as Earth becomes a highly reflective object in space. The planet would appear as a bright, featureless white sphere to any theoretical observer. Earth's appearance from space transforms completely. Seismic activity continues from internal geological processes. Though surface detection becomes difficult through layers of ice and frozen atmosphere, earthquakes still occur, but their surface effects are muted by the frozen layers covering the ground. Archaeological preservation becomes perfect as all organic and inorganic materials freeze in place permanently. The frozen planet becomes a museum of its former living state, with all materials preserved indefinitely in the extreme cold. By the end of the first year, Earth has completed its transformation from a living world to a frozen monument. The ice ball that was once humanity's home continues orbiting the dark Sun, carrying within its frozen layers the preserved remains of the most remarkable biological experiment in the known universe. The Sun that has sustained life for billions of years operates through nuclear fusion, the same process that powers hydrogen bombs, but controlled and sustained at stellar scales. Understanding stellar physics reveals why our Sun cannot simply stop shining and helps explain the remarkable stability of the fusion process. Nuclear fusion in the Sun's core combines hydrogen atoms into helium, releasing tremendous energy through Einstein's famous equation, E equals mc squared. 4 hydrogen nuclei fuse to create one helium nucleus, with the mass difference converted to energy. This process occurs at temperatures of 15 million degrees Celsius and pressures 250 billion times Earth's surface pressure. Stellar structure maintains perfect balance between gravitational collapse and radiation pressure. The Sun's own gravity tries to crush it into a point, while nuclear fusion creates outward pressure that resists collapse. This hydrostatic equilibrium has remained stable for 4.6 billion years and will continue for billions more. Convection zones transport energy from the fusion core to the surface through massive circulation cells. Hot plasma rises from interior regions while cooler material sinks, creating circulation patterns larger than entire planets. This convection process takes thousands of years to transport energy from core to surface. Photon transport through the sun's interior involves a random walk process where individual light particles bounce between atoms millions of times before reaching the surface. A photon created in the core might take 100,000 years to reach the surface, traveling a path trillions of times longer than the sun's radius. Main sequence stability means our sun belongs to a class of stars that maintains steady fusion rates for billions of years. The sun has consumed less than half its hydrogen fuel and will continue shining at current levels for approximately 5 billion more years. Stellar physics provides remarkable long-term energy security. Feedback mechanisms prevent runaway fusion reactions that could destabilize the sun. If fusion rates increase, the core heats up and expands, reducing pressure and slowing fusion. If fusion slows, gravity compresses the core, increasing pressure and accelerating fusion. These automatic controls maintain stellar stability. Solar neutrinos produced by fusion reactions stream through Earth continuously, providing direct evidence that nuclear fusion operates normally in the sun's core. Neutrino detection experiments confirm that fusion reactions proceed at expected rates, verifying our understanding of solar energy production. Magnetic field generation in the sun creates solar weather patterns and sunspot cycles, but these surface phenomena don't affect core fusion processes. Solar storms and magnetic activity represent surface effects rather than fundamental changes in the sun's energy production mechanisms. Conservation of energy laws make it impossible for the sun to suddenly stop producing energy without violating fundamental physics. The nuclear fuel exists in the core, the temperature and pressure conditions support fusion, and no known mechanism could instantly halt these reactions across the sun's massive volume. Stellar evolution follows predictable patterns based on stellar mass and composition. Our sun will eventually exhaust core hydrogen and evolve into a red giant star, then a white dwarf. But these changes occur over billions of years, not suddenly. Stellar physics operates on geological timescales, not human timescales. Nuclear physics prevents the sun from simply turning off like a light switch. Fusion reactions occur in the core due to quantum tunneling effects that allow hydrogen nuclei to overcome electrical repulsion at specific temperatures and pressures. These conditions cannot change rapidly enough to halt fusion suddenly. Stellar collapse would occur if fusion stopped, but this process would actually generate more energy rather than less. Gravitational collapse converts gravitational potential energy into heat, initially making the star brighter rather than darker. Stellar death involves increased energy output, not sudden shutdown. Observational evidence from other similar stars confirms that sun-like stars maintain stable energy output for billions of years. Astronomical observations show that main sequence stars like our Sun behave predictably and maintain steady luminosity throughout their long lifetimes. Helioseismology, the study of solar oscillations, allows scientists to probe the Sun's interior structure and confirm that fusion processes operate normally. Solar oscillations provide direct evidence that the Sun's interior matches theoretical predictions for stellar structure and energy production. Mass energy conversion in stellar fusion represents the most efficient energy production process known in nature. Fusion converts approximately 0.7% of hydrogen mass into energy, far more efficient than chemical reactions. The Sun has sufficient fuel to maintain current energy output for billions more years. Stellar formation processes create stars with compositions and structures that naturally support stable fusion for extended periods. The Sun formed from gas clouds with optimal hydrogen content and gravitational mass to sustain long-term fusion reactions. Quantum mechanics governs fusion reactions at the particle level, determining reaction rates and energy production. These quantum processes operate according to fundamental physics laws that cannot be altered by external conditions affecting the Sun's surface or solar system environment. Solar constant measurements show that the Sun's energy output varies by less than 0.1% over solar cycles, demonstrating remarkable stability in fusion energy production. This consistency over centuries of measurement confirms that solar energy production remains essentially constant. Comparative stellar astronomy reveals that our Sun represents a typical, stable star that will continue normal operation for billions more years. The physics of stellar evolution and nuclear fusion provide strong assurance that Earth's energy source will remain reliable far beyond any human timescale. Our Sun follows a stellar evolution path mapped out by astrophysics with remarkable precision. The timeline of our star's life spans billions of years, making human civilization a brief moment in solar history. Understanding this timeline reveals both the remarkable stability we enjoy and the eventual challenges our descendants will face. Main sequence lifetime extends approximately 10 billion years total for a star of our Sun's mass. The Sun has already spent 4.6 billion years in stable hydrogen fusion and has roughly 5 billion years remaining in this phase. This timeframe exceeds the entire history of complex life on Earth by orders of magnitude. Hydrogen burning in the core proceeds at carefully controlled rates determined by stellar mass and composition. Core temperatures of 15 million Kelvin maintain fusion reactions that convert 600 million tons of hydrogen into helium every second. Despite this massive consumption rate, the Sun contains enough hydrogen to continue for billions more years. Luminosity increases gradually over the main sequence lifetime as helium accumulates in the core, increasing central temperature and fusion rates. The Sun has become approximately 30% brighter since Earth formed. This gradual brightening will continue, eventually making Earth uninhabitable even while the Sun remains stable. Red giant phase begins when core hydrogen becomes depleted and fusion moves to a shell surrounding the helium core. The Sun will expand dramatically, possibly reaching Earth's orbit. Surface temperature will decrease while total luminosity increases tremendously. This phase represents the beginning of the Sun's death process. Helium flash occurs when core temperature reaches 100 million Kelvin and helium begins fusing into carbon and oxygen. This process happens rapidly compared to hydrogen fusion, lasting only about 100 million years. The helium burning phase provides temporary stability before the final stellar evolution phases. Asymptotic giant branch phase involves alternating hydrogen and helium shell fusion as the star becomes increasingly unstable. Thermal pulses create periodic brightness variations and mass loss through stellar winds. The Sun will lose significant mass during this phase, affecting planetary orbits. Planetary nebula formation occurs when the Sun ejects its outer layers, creating a glowing shell of gas surrounding the remaining stellar core. These beautiful astronomical objects represent stellar death, though the process takes thousands of years to complete. Earth might survive within the expanding nebula shell. White dwarf remnant represents the Sun's final state. A hot, dense core, roughly Earth-sized, but containing most of the Sun's mass. White dwarf stars cool slowly over trillions of years, far longer than the current age of the universe. This stellar corpse will outlast galaxies and normal stellar formation. Planetary effects during solar evolution will dramatically alter conditions in the solar system long before the Sun dies. Increasing solar luminosity will boil Earth's oceans in approximately 1 billion years. The habitable zone will move outward, potentially making Mars and the outer moons habitable. Timeline uncertainty exists in stellar evolution models, but the uncertainties involve millions rather than billions of years. Stellar physics provides reliable predictions for solar evolution, though precise timing depends on complex internal processes that cannot be observed directly. Comparison with other stars confirms solar evolution models through observations of stars at different evolutionary stages. We can observe stars similar to the Sun at various phases of stellar evolution, providing observational confirmation of theoretical predictions about our Sun's future. Human timescales provide perspective on stellar evolution rates. All of recorded human history spans less than 10,000 years, while the Sun's remaining stable lifetime exceeds 5 billion years. Human civilization could evolve and develop for millions of generations before facing any threat from solar evolution. Technological development timelines suggest that human civilization will become unrecognizably advanced long before solar evolution threatens Earth's habitability. The time available for technological development far exceeds any reasonable projection of human advancement rates. Galactic context shows that solar evolution represents normal stellar behavior rather than exceptional circumstances. The Sun belongs to a common class of stars with well-understood evolution patterns. Solar death represents natural stellar processes rather than cosmic accidents. Climate evolution on Earth will be driven by increasing solar luminosity over hundreds of millions of years, gradually making the planet warmer and eventually uninhabitable for current life forms. However, biological evolution and technological development provide ample time for adaptation. Energy reserves in stellar fusion provide perspective on energy abundance compared to human consumption. The Sun produces more energy in 1 second than human civilization has consumed throughout its entire existence. Solar energy represents effectively unlimited abundance on human timescales. Survival strategies for far future humans might include moving Earth to a more distant orbit, building massive solar shields, or relocating to other star systems. The billions of years available for development provide extensive time for developing technologies to address solar evolution challenges. Alternative energy sources become relevant only on stellar evolution timescales, far beyond any current energy concerns. Fusion power, if developed, could theoretically outlast the Sun itself by using stellar material or interstellar hydrogen as fuel sources. Philosophical implications of solar longevity include the remarkable stability and reliability of Earth's energy source compared to human planning horizons. The Sun provides energy security that extends far beyond any other resource planning considerations for human civilization. The real solar timeline reveals a star that will reliably provide energy for timescales that make human concerns about energy sustainability seem almost trivial by comparison. Our Sun represents the ultimate long-term energy investment for human civilization. While the Sun cannot simply turn off, the universe contains genuine threats that could affect solar energy reaching Earth, or even damage the Sun itself. These cosmic catastrophes represent the real dangers that could create conditions similar to our thought experiment. Gamma-ray bursts represent the most energetic events in the known universe, releasing more energy in seconds than the Sun produces in millions of years. A nearby gamma-ray burst could strip away Earth's ozone layer, exposing the surface to lethal radiation while disrupting atmospheric chemistry for years. Supernovae within 50 light-years of Earth could deliver radiation doses that would devastate the biosphere. While not stopping the Sun, a nearby supernova would damage Earth's atmosphere and potentially trigger mass extinctions. The radiation pulse could also affect solar system dynamics through gravitational wave effects. Rogue planets, ejected from other star systems, could potentially pass through our solar system and gravitationally disrupt planetary orbits. A massive rogue planet could alter Earth's orbit, moving it farther from the Sun and creating conditions similar to permanent winter. Solar minimum periods represent natural variations in solar activity that could affect Earth's climate. During extended solar minimum events, the Sun's energy output decreases by small but measurable amounts, potentially contributing to ice age conditions on Earth. Interstellar dust clouds could block significant amounts of sunlight if the solar system passed through dense regions of the galaxy. These dust clouds could reduce solar energy reaching Earth while not affecting the Sun's energy production. Dense molecular clouds represent a more serious version of this threat. Asteroid impacts could create conditions similar to nuclear winter by ejecting massive amounts of dust into Earth's atmosphere. While not affecting the Sun, asteroid impacts could block sunlight from reaching Earth's surface for months or years, creating temporary conditions similar to our scenario. Volcanic winter scenarios involve massive volcanic eruptions that inject sulfur and ash into the stratosphere, reducing sunlight reaching Earth's surface. Supervolcanic eruptions like Yellowstone or Toba could create global cooling lasting several years. Solar flares and coronal mass ejections could damage Earth's electrical systems and satellite networks. though they would not reduce the sun's energy output. Extreme solar storms could disrupt technological civilization, while leaving the sun's fusion processes unaffected. Magnetic pole reversals on the sun could alter the solar wind and affect Earth's magnetosphere, potentially exposing the planet to increased radiation. While not stopping solar fusion, magnetic field changes could affect how solar energy interacts with Earth's atmosphere. Galactic cosmic ray increases during the solar system's passage through spiral arms could affect cloud formation and climate patterns on Earth. Increased cosmic ray flux might trigger ice age conditions through changes in cloud cover and atmospheric chemistry. Black hole encounters represent extremely unlikely but theoretically possible threats to the solar system. A passing black hole could gravitationally disrupt planetary orbits, or even affect the sun's structure, though such encounters are extraordinarily rare. Dark matter interactions, if they affect stellar fusion processes, could theoretically alter the sun's energy production. However, dark matter interactions with normal matter appear to be extremely weak, making this an unlikely threat to solar stability. Alien intervention represents speculative but conceivable scenarios where advanced technological civilizations could affect stellar energy output. Hypothetical megastructures around stars could block sunlight from reaching planets, creating artificial conditions similar to solar shutdown. Vacuum decay events, if they exist, could fundamentally alter the laws of physics in expanding regions of space. Such events would affect all matter and energy, including stellar fusion processes. However, vacuum decay remains highly speculative and unconfirmed by current physics. False vacuum collapse scenarios suggest that the universe might exist in a metastable state that could spontaneously transition to a lower energy state, altering fundamental physics. Such transitions would affect stellar fusion and all other physical processes simultaneously. Probability assessments for cosmic catastrophes vary enormously depending on the specific threat. Asteroid impacts occur regularly on geological timescales. Gamma-ray bursts and supernovae within dangerous distances are much rarer. Some theoretical threats may be impossible or extremely unlikely. Detection capabilities for cosmic threats have improved dramatically with modern astronomy. Surveys monitor potentially hazardous asteroids. Telescopes observe supernovae in other galaxies. Satellite networks monitor solar activity. Early warning systems provide some protection against known threats. Mitigation strategies exist for some cosmic threats, but not others. Asteroid impacts could theoretically be prevented or deflected with sufficient advance warning. Solar storms can be prepared for by shutting down electrical systems. Other threats exceed current technological responses. Historical examples of cosmic catastrophes include the Cretaceous-Paleogene extinction, possibly caused by asteroid impact, the Permian extinction, possibly triggered by volcanism, and smaller events like the Tunguska impact and Carrington solar storm. Research priorities focus on understanding and preparing for the most likely cosmic threats rather than speculative scenarios. Asteroid detection and deflection receive significant funding. Solar storm monitoring has practical applications. Gamma-ray burst research remains primarily theoretical. Unlike our thought experiment of sudden solar shutdown, real cosmic catastrophes typically provide some warning time and affect Earth through indirect mechanisms rather than completely stopping solar energy production. Understanding these real threats provides perspective on both cosmic dangers and the remarkable stability of our solar energy source. The physics of stellar fusion make it impossible for the sun to suddenly cease energy production. Understanding why reveals the remarkable engineering of stellar structure and the conservation laws that govern energy production in stars. Conservation of energy dictates that energy cannot be created or destroyed, only converted from one form to another. The sun's energy comes from nuclear fusion converting mass into energy. For fusion to stop suddenly, this mass would need to disappear instantly, violating fundamental physics laws. Nuclear reaction rates depend on temperature and pressure conditions that change slowly over stellar lifetimes. The Sun's core temperature of 15 million Kelvin and pressure 250 billion times Earth's surface pressure create conditions where fusion occurs naturally. These conditions cannot change rapidly enough to halt fusion suddenly. Stellar structure maintains automatic stability through hydrostatic equilibrium. If fusion rates decreased, gravitational collapse would increase core temperature and pressure, accelerating fusion. If fusion rates increased, radiation pressure would expand the core, reducing temperature and pressure, slowing fusion. These feedback mechanisms prevent sudden changes. Quantum tunneling effects that enable fusion operate according to fundamental physics principles that cannot be altered by external conditions. Hydrogen nuclei overcome electrical repulsion through quantum mechanical effects that depend only on temperature, pressure, and nuclear physics constants. Thermal inertia in stellar cores means that temperature changes require enormous energy inputs over extended time periods. The Sun's core contains the mass of several Earth-sized objects at extreme temperature and pressure. Cooling this material would require energy removal on planetary scales over millions of years. Energy transport timescales from core to surface involve processes taking thousands of years. Even if fusion somehow stopped instantly in the core, the Sun would continue shining for thousands of years as stored energy continues flowing outward through convection and radiation. Stellar observations of thousands of Sun-like stars show no examples of sudden cessation of energy production. Stars experience gradual evolution over billions of years, or catastrophic collapse that actually increases energy output initially. No known stellar process causes sudden energy shutdown. Nuclear fuel abundance ensures continued fusion for billions of years. The Sun's core contains enough hydrogen to maintain current fusion rates for approximately 5 billion more years. Nuclear fuel depletion occurs gradually over geological timescales, not suddenly. Magnetic field effects, while creating surface phenomena like sunspots and solar flares, do not affect core fusion processes. Stellar magnetic fields operate in outer layers, while fusion occurs in inner regions under conditions dominated by gravity and nuclear physics rather than magnetism. Gravitational collapse scenarios actually produce more energy rather than less. If something caused the Sun's structure to become unstable, gravitational collapse would convert gravitational potential energy into heat, initially making the star brighter and hotter rather than darker and cooler. Chemical composition changes occur slowly through nuclear fusion processes that gradually convert hydrogen to helium over billions of years. The Sun's composition cannot change rapidly enough to affect fusion conditions significantly over short timescales. External influences cannot significantly affect stellar fusion rates. Solar system objects, including planets and asteroids, possess insufficient mass to gravitationally influence solar core conditions. Interstellar dust or gas clouds could affect sunlight reaching Earth, but not solar energy production. Phase transitions in stellar matter require extreme conditions that develop gradually over millions of years. Stellar evolution involves predictable phase changes as nuclear fuel becomes depleted. But these transitions occur slowly and actually involve increased energy production during transition phases. Quantum mechanics principles governing nuclear fusion operate according to fundamental physics constants that cannot be altered by conditions in the solar system or local galactic environment. Nuclear fusion rates depend only on particle physics and thermodynamics, not external astronomical conditions. Stellar stability research confirms that main sequence stars like the Sun maintain steady energy output through automatic regulation mechanisms. Stellar physics models based on well-understood nuclear and gravitational physics predict stable fusion for billions of years. Energy production efficiency in stellar fusion exceeds any human energy production methods by factors of millions. Nuclear fusion converts mass to energy with 0.7% efficiency, far higher than chemical reactions. This efficiency ensures steady energy production from relatively small amounts of nuclear fuel. Observational evidence from helioseismology confirms that the Sun's interior structure matches theoretical predictions for stable fusion. Solar oscillations provide direct measurement of internal conditions, verifying that fusion processes operate normally and will continue operating normally. Comparative astronomy shows that sun-like stars throughout the galaxy maintain stable energy production for periods measured in billions of years. Our Sun represents a typical example of stellar engineering that has proven reliable throughout cosmic history. Physics constraints make stellar energy production remarkably robust against external influences. The same physics that makes nuclear weapons powerful ensures that stellar fusion cannot be easily disrupted once established in stellar cores under appropriate temperature and pressure conditions. The Sun's reliability as an energy source exceeds any human engineering achievement by factors of billions in both power output and operational lifetime. Understanding stellar physics reveals why our Sun provides the most dependable energy source available to human civilization. Every morning, 93 million miles away, the most remarkable engineering project in our solar system awakens for another day of operation. 400 trillion watts of power generation, operating continuously for over 4 billion years with perfect reliability. The Sun rises not as a simple astronomical event, but as a daily miracle of physics. Nuclear fusion in the Sun's core converts 600 million tons of hydrogen into helium every second, releasing energy equivalent to billions of nuclear power plants operating simultaneously. This process has continued without interruption since before Earth formed, providing the energy that made life possible and sustaining it through every evolutionary milestone. The light that reaches Earth each morning began its journey in the Sun's core perhaps 100,000 years ago, traveling randomly through the stellar interior before finally streaming across space at 186,000 miles per second. Every photon that warms your face has been traveling for millennia just to reach this moment. Temperature regulation from our solar energy source maintains Earth's surface temperature within the narrow range where water remains liquid and life can flourish. Without this steady input of energy, our planet would be an ice ball with surface temperatures approaching absolute zero within a single year. Atmospheric circulation, weather patterns, and climate all depend on solar energy creating temperature differences that drive air movement and precipitation. The water cycle that brings rain to crops and fills reservoirs operates entirely on solar power, evaporating water from oceans and moving it across continents. Photosynthesis, the process that produces oxygen and captures carbon from the atmosphere, converts solar energy into chemical energy that forms the foundation of all food webs. Every breath of oxygen you take was produced by plants using solar energy to split water molecules and release oxygen gas. Human civilization exists entirely within the solar energy budget. Fossil fuels represent stored ancient sunlight. Wind power captures solar energy converted to atmospheric motion. Hydroelectric power uses solar energy that evaporated and precipitated water to higher elevations. Even nuclear power came from elements forged in previous generations of stars. Agricultural productivity depends completely on solar energy driving photosynthesis that creates the carbohydrates, proteins, and other molecules that become food. The sun powers every biological process that produces human nutrition, from the smallest grain of wheat to the largest fruit tree. Economic activity operates within the flow of solar energy through Earth's systems. International trade moves goods created through solar-powered processes. Manufacturing reshapes materials extracted and processed using energy originally derived from sunlight. Commerce represents human organization of solar energy flows. Cultural development throughout human history has been shaped by solar cycles and seasonal changes. Architecture designed for solar orientation, religious ceremonies celebrating solstices and harvests, artistic traditions inspired by light and shadow all reflect humanity's deep connection to solar energy. Scientific understanding has revealed the elegant physics behind solar energy production, from nuclear fusion to electromagnetic radiation to biological energy conversion. Each discovery deepens appreciation for the complex processes that make solar energy available for life on Earth. Technological progress in solar energy utilization represents humanity's direct partnership with stellar engineering. Solar panels convert sunlight directly into electricity. Solar thermal systems capture heat for buildings and industrial processes. Advanced solar technologies promise even greater efficiency in capturing stellar energy. Environmental stewardship becomes more meaningful when understood as managing the flow of solar energy through Earth's systems. Climate change results from altering how solar energy moves through atmospheric and biological systems. Environmental protection preserves the natural systems that capture and distribute solar energy. Future possibilities expand as human understanding of solar energy deepens and technology improves. Space-based solar power could capture solar energy without atmospheric interference. Artificial photosynthesis could enhance natural energy capture. Solar energy provides the foundation for sustainable human development. Cosmic perspective reveals Earth as a small planet, perfectly positioned in the habitable zone around a stable star. The distance from Sun to Earth creates surface temperatures ideal for liquid water and biological processes. This orbital position represents an extraordinary astronomical coincidence that enables life as we know it. Gratitude for solar reliability grows from understanding how precisely balanced stellar physics must be to maintain stable energy output for billions of years. The Sun's mass, composition, and nuclear processes create conditions that provide steady energy output over timescales that dwarf human experience. Daily appreciation for sunrise becomes deeper when informed by knowledge of the incredible processes that make dawn possible. Each morning represents the successful completion of another day's nuclear fusion, electromagnetic radiation transport, and energy delivery across interplanetary space. Wonder at natural processes intensifies when understanding the complexity behind apparently simple phenomena. Sunlight appears effortless, but represents the culmination of quantum mechanics, nuclear physics, plasma dynamics, and electromagnetic theory operating at stellar scales. The next time dawn breaks over your horizon, remember that you're witnessing the arrival of energy that began its journey in the heart of a star, traveled for millennia through stellar plasma, then raced across 93 million miles of vacuum to warm your world and power your life. In our thought experiment, we explored the consequences of losing this stellar gift. But every real morning proves that the gift continues, that fusion burns steady in the solar core, that Earth continues its precise orbital dance in the habitable zone. The sun will rise tomorrow and for billions of tomorrows after that. In the face of this cosmic reliability, human concerns about energy security seem almost trivial. We are powered by a star, heated by fusion, sustained by the most dependable energy source in the known universe. Tomorrow's dawn carries with it 4.5 billion years of stellar evolution, the energy that powers all life on Earth, and the promise of 5 billion more years of reliable sunshine. Perhaps that's something worth waking up early to witness.